Use theorem 5.2.1 and the result of exercise 10 to prove that if p is any prime number with p greater than or equal to 5, then the sum of the squares of any p consecutive integers is divisible by p. Now here I have theorem 5.2.1 and here I have exercise 10. So now we have to write the sum of the squares of any p consecutive integers. This is going to be a little bit tricky because the formula is going to look a little weird. So I'm going to let a squared be the first square in this series. So our series is going to look something like a squared plus a plus 1 squared plus a plus 2 squared, and so on. But let's use some summation notation here. K is going to be my index variable, which is going to vary from 0 to p minus 1. The reason I'm going from 0 to p minus 1 is because the formula for the basis here is going to be a little convenient. If I write my base as a plus k, and then I square that, this will be a simple rule to determine the base of each term in the series, depending on my index variable k. And so we need to evaluate what this is. And we need to show that when we evaluate this, we're going to be able to factor out a p, which means that this will be divisible by p. So the first thing I'm going to do is I'm going to FOIL this term here, a plus k, with itself. So this is going to be a squared plus 2ak plus k squared. Next, I can rewrite this series as the sum of 3 different series here corresponding to 3 different formulas. So the first series is just going to be from k equals 0 to p minus 1 of a squared. The next formula is going to be from k equals 0 to p minus 1 of 2ak. And then lastly, we have a sum from k equals 0 to p minus 1 of k squared. For the first series, we can pull out the a squared and write this as the sum from k equals 0 to p minus 1 of just 1, which is really easy to compute. We'll do that in a second. For the second series, I'm going to pull out 2a since those are not dependent on my index variable here. And so the formula for this series is now just k. And for this other series, we can actually use exercise 10. Now keep in mind that when I plug in k equals 0 into this series, it's just 0 squared, which means that starting at k equals 0 is the same thing as starting at k equals 1 for this particular series. The same is true about this series, which we'll get into in a second. But that means that I can imagine this as 0 squared plus 1 squared plus 2 squared plus 3 squared, which is the same thing as this, all the way to plus n squared. But the last number for my index variable is going to be p minus 1. So for this formula, I'm going to replace n with p minus 1. So this is going to be p minus 1 times p minus 1 plus 1, which is just p, and then times 2 times p minus 1 plus 1, all over 6. Next, we can simplify this summation. This is just 1 plus 1 plus 1 plus 1 plus 1 over and over again. How many times? Well, there are p terms in each of these series, which means that this is just a squared times p. For the last series here, we can use theorem 5.2.1, which tells us that the sum of the first n integers is n times n plus 1 over 2. But in this case, we're going up to p minus 1, which means the formula is going to be p minus 1 times p minus 1 plus 1, which is just p, all over 2. And then I'll simplify this other fraction here. And then lastly, we can factor out a p from each of these 3 terms and write this as p times a squared. These 2's cancel, and so this is plus a times p minus 1. And then plus, this is going to be p minus 1 times 2p plus 1 all over 6. Now keep in mind that p is a prime number greater than or equal to 5. And we already know that this number here is going to result in an integer. But what happens when I pull out a factor of p? Does that mean that this is now a fraction? We have to consider that case because in order to prove that this number is divisible by p, we have to be able to factor out a p, and everything else has to be an integer. But if this is not an integer, then we're not done yet. So we have to justify why this is an integer. And the reason is because p is a prime number. So let me just say something real quick. Now since p is a prime number and p is greater than or equal to 5, that means the greatest common divisor between 6 and p is going to be 1, which means I can factor out this p and and then everything left over is going to still be an integer. And that's because this original fraction is an integer. P minus 1 times p times 2p plus 1 all over 6 is an integer, since this is the result of a summation of integers. So this means that if we let x equal a squared plus a times p p minus 1 plus p minus 1 times 2p plus 1 all over 6 is an integer. So that means if I take a squared plus a plus 1 squared, and I do this p times, all the way up to a plus p minus 1 squared, this is equal to p times x, which means p divides the sum. And that's our proof. Thanks, everyone, and I'll see you in the next video.